Hello, I'm Anupama Rai, and today I'm going to present on convex optimization with matrices. So, these are the contents that I'm going to talk about. So, first, let's start with introduction to optimization. Optimization is a fundamental concept in mathematics, computer science, engineering, and economics that deals with the process of making the best possible decision from a set of available choices. In simple terms, it refers to finding the most efficient, cost effective, beneficial solution to a problem while adhering to certain rules or constraints. The best solution may mean achieving the minimum possible value, such as minimizing cost, error, or energy, or the maximum possible value, such as maximizing profit, accuracy, or efficiency. At the heart of optimization lies the idea of balancing objectives with restrictions. The objective functions, usually denoted as fx, represents the quantity we wish to minimize or maximize, while the feasible reason C defines all possible solutions that satisfy the problem's constraints. The mathematical form of an optimization problem is often expressed as minimize f of x over all x belonging to R to the power n, subject to x belonging to feasible reason C, where x is the decision variable belonging to the n-dimensional real space, fx is the functional to optimize, and C represents the set of permissible solutions. There are several ways to classify optimizations, optimize, depending on the structure of the objective function and the feasible reason. So, the major types of optimization being linear and nonlinear optimization, and convex and non-convex optimization. So, let's first start with linear and nonlinear optimization. In linear optimization, we usually deal with problems where the relationships are linear. A classic example is solving an overdetermined linear system where we have more equations than unknowns. Mathematically, this can be written as Fm equals to Ft, where F is a known matrix, M is the vector of unknowns, and D is a non-vector. Since the system is overdetermined, we can't find an exact solution that satisfies all equations. So instead, we try to minimize the squared residual error. The solution to this minimization problem is obtained by solving the equation called the normal equations, which is represented as F transpose times F times M equals F transpose times T. Now, talking about the nonlinear optimization, it's either the objective function or the constraints, or sometimes both, are nonlinear. The goal is still to minimize or maximize a function, but the process is far more complex. Suppose we have an objective function, Jm. We want to find a value of m that minimizes Jm because the function is nonlinear. We cannot directly solve it with a neat formula like in the linear case. Instead, we use iterative methods, approaches that improve the solution step by step. This typically involves choosing a source direction, like steepest descent or Newton's direction, performing a line search along the directions to find how far to move, repeating the process until convergence is achieved. And the optimality condition is usually expressed as the gradient of j at m star equals 0. This means that at the optimum point, the slope of the function is flat. No further decrease is possible in any directions. So the key difference between linear and nonlinear optimization is that linear optimization is structured with quadratic objectives derived from linear systems and is often solvable using analytical solutions, while nonlinear optimization is much more general, requiring iterative numerical techniques, convergence criteria, and sometimes approximate solutions. In short, linear optimization gives us direct, predictable results, while nonlinear optimization gives us flexibility to model real world problems but demands more sophisticated strategies. So, optimization problems can also be classified as convex or non convex based on the shape of the objective function and the feasible reason. This classification is extremely important because it determines how easy or difficult it is to find the best solution. So, first, convex optimization. A problem is called convex optimization if two conditions hold. First condition being that the objective function is a convex. And secondly, the feasible reason, that is, the set of all allowable solutions, is a convex set. So, now what does convex mean? A function fx is convex if for any 2 points x1 and x2 and for any value of lambda between 0 and 1, the following condition holds. The function at lambda times x1 plus 1 minus lambda times x2 is less than or equal to lambda times f of x1 plus 1 minus lambda times of x2. Geometrically, this means the line segment between any 2 points on the graph of the function always lies above the curve. This property ensures that the function curves upward like a bow. The big advantage of convex optimization is that any local minimum is automatically a global minimum. This means if you find one point where the slope flattens out, you can be confident that it is the absolute best solution. Because of this, convex optimization is generally much easier to solve reliability. Now, in contrast, non-convex optimization occurs when either the objective function or the feasible region is non-convex. This function can have a much more complicated shape, often with multiple valleys and peaks. This means the function can have multiple local minima. The, those points that look like the lowest value in the neighborhood but are not the lowest overall, and multiple local maxima. Those points that look like the highest value nearby but not globally. As a result, algorithms can easily get trapped in one of those local optima instead of finding the true global solutions. To handle this challenge, researchers use more advanced techniques such as simulated annealing, genetic algorithms, or other evolutionary methods, which are designed to explore the search space more broadly and avoid being stuck in local solutions. Now, the key difference between convex optimization and non-convex optimization is that convex optimization guarantees global optimality and is straightforward to solve using gradient based methods and is very reliable. In contrast, non convex optimization is more realistic in many real world problems but difficult to solve because of multiple local optima, which requires advanced algorithms and careful tuning. A very important building block in optimization theory is the idea of convex sets. Whether the feasible region of an optimization problem is convex or not often decides how easy or difficult the problem will be to solve. So, formally a set C is convex for any 2 points x and y inside the set. The entire line segment joining these 2 points also lies inside the set. Mathematically, this is written as for any lambda between 0 and 1, lambda times x plus 1 minus lambda times y also belongs to the set C. The simple condition guarantees that convex sets have no gaps or holes. If you pick if you pick 2 points in the set, everything in between is also included. So now talking about this image illustrates this idea beautifully. On the left side, we see a convex set as 2 points x and y are chosen inside this set. The line segment xy connecting them lies completely inside the region. This satisfies the convexity condition. On the right side, we see a non-convex set as again 2 points x and y are chosen, but this time the connection line xy goes partly outside the set. Since the set does not contain the entire line segment, it is non-convex. So the key takeaway from the image is convex sets always contains the straight line between any 2 points, while non-convex sets do not. So now some of the examples of convex sets are simple geometric shapes like circles, squares, triangles, and ellipses, or any polygon without indentations, half spaces such as all points satisfying A transpose X is smaller than or equals to B. Also, for example, some of the examples of non-convex sets are shapes with indentation such as crescent moons, stars, L shapes or U shapes, similar union of separate regions, etc. As we talked about convex sets, we also have the concept of convex functions, which play a central role in optimization. So a function fx is convex if for any 2 points x1 and x2 and for any value of lambda between 0 and 1, the following condition holds. The function At lambda times x1 plus 1 minus lambda times x2 is less than or equal to lambda times f of x1 plus 1 minus lambda times f of x2. Geometrically, this means that if you draw a straight line between 2 points on the curve of the function, the line will always lie above or on the graph of the function. In other words, the function spins upward like a ball. Some of the key properties of convex functions are the most important property of convex function is that any local minimum is also a global minimum. This makes convex function extremely powerful in optimization because once you find a point where the function stops decreasing, you can be certain that it's the best possible solution overall. Some of the examples of convex function are quadratic equation fx equals to x to the power 2. This is the parabola which opens upwards. Exponential functions fx equals to e to the power x. It's always convex and keeps rising faster. Absolute value function fx equals to more x, which creates a V shape, which is convex even though it's not smooth at 0. These, ep- these examples illustrate that convex functions can be smooth like a parabola or non-smooth like the absolute value and still satisfy convexity. Convex functions are the backbone of convex optimization. They give us a guarantee that the solutions we find are not just locally good but globally optimal. This is why they are widely used in machine learning, economics, engineering, and many other fields. So, now talking about the convex optimization problem formulation. A convex optimization problem is a special cases class of optimization problems that can be solved efficiently because of its unique mathematical structure. The general form is minimize fx subject to gix which is smaller or equals to 0. It's an inequality constraint and at jx equals to 0 equality constraints. Here, fx is the objective function we want to minimize. Jx are the inequality constraints, each of which must be convex to ensure the feasible region is convex. Jx are the equality constraints, which must be affine functions of the form Jx equals to Az transpose x plus Bz. So, some of the requirements for convexity to qualify as a convex optimization problem, the following must be held. First, objective function fx must be convex. Inequality constraints gix must be convex functions. Equality constraint hjx must be affine, meaning linear in nature. So, the examples of convex optimization problems. First is linear programming. Linear programming problem is one of the simplest and most widely used forms of convex optimization. It is defined as minimize C transpose X subject to AX which is smaller than or equals to B, EX equals to D, where C is a coefficient vector for the objective function, A and E are constraint matrices, B and D are vectors representing bounds. Linear programming is used in scheduling, resource allocation, transportation planning, and supply chain management. While now talking about the quadratic programming extends linear programming by allowing the objective functions to be quadratic. While the constants remain linear, it is formulated as minimize 1 by 2 x transpose t qx plus c transpose x subject to ax is less than or equals to b, ex equals to d, where q is a positive semi-definite matrix to ensure convexity, c is a vector of coefficients, a, b, e, d are defined as linear programming. Now, quadratic programming is commonly used in portfolio optimization, uh, meaning minimizing financial risk, machine learning, such as support vector machines and control systems. More on quadratic programming, it is a class of optimization problems where the objective function is quadratic and the constraints are linear. It serves as a natural generalization of linear programming and has widespread application in different fields. So, the general matrix form of a quadratic programming problem can be expressed as Minimize f of x equals 1 half x transpose q x plus c transpose x subject to ax less than or equals to b ex equals to d. So now let's talk about the roles of Q matrix in quadratic programming. So the matrix Q captures the curvature of the quadratic norm. For the optimization problem to be convex, the matrix Q must be positive semi-defined. This condition ensures that the objective function is bowl-shaped, so any local minimum is guaranteed to be the global minimum. If Q is positive definite, the problem has a unique minimizer. On the other hand, if Q is indefinite, containing both positive and negative eigenvalues, the problem becomes non-convex. Non-convex QPs are significantly harder to solve because they may have multiple local minima and finding the global solution is generally hard. The factor of 1 by 2 in front of X transpose QX is purely a mathematical convenience. It simplifies the gradient of the objective function without introducing an unnecessary coefficient of 2. So now about the convexity and optimality. Convexity plays a central role in quadratic programming. Convex QP, any feasible local minimum is automatically the global minimum. Efficient algorithms such as interior point methods or active state methods can be applied with guaranteed conversions. Non-con- Non-convex QP, Q indefinite. The problem may have multiple minima, saddle points, or maxima. Global optimization techniques or heuristics like brands and boundary evolutionary algorithms are often required, making the problem computationally demanding. Thus, the condition Q positive definite Q semi positive semi-definite is what makes quadratic programming both tractable and widely applicable in practice. So now talking about the properties, first convexity check. A quadratic function is written as f of x equals 1 half times x transpose qx plus c transpose x plus r. The convexity of this quadratic function is completely determined by the matrix Q. If Q is positive semi-definite, written as Q greater than or equals to 0 with the semi-definite symbol, then f of x is convex. If Q is positive definite, written as Q strictly greater than 0, then f of x is strictly convex. In short, Q semi-definite means convex and Q definite means strictly convex. Now, the existence of global optima. In convex optimization, every local minimum is also a global minimum. If the feasible region defined by the constraint is non-empty and closed, and if the objective function is convex, then a global solution is guaranteed to exist. By contrast, in non-convex optimization, the functions may have multiple local minima. Solvers can get stuck at one of these points without ever finding the true global minima. Now, the uniqueness of the solution. If Q is positive definite, meaning Q is strictly greater than 0, then the function is strictly convex. That guarantees that the global optimum is unique. On the other hand, if Q is only positive semi-definite, then the function is convex but not strictly convex. In this case, multiple optimal solutions may exist. A typical example is when the function has a flat valley where many points along that valley achieve the same minimum value. So the mathematical tools that can be used are first gradients. It's a first order conditioned one. So for a quadratic function, f of x equals 1 half x transpose qx plus c transpose x. The gradient will be the gradient of f of x equals qx plus c. It's a order optimality condition. It differentiable f with convex domain. It's convex if f of y is greater than or equal to f of x plus the gradient of f of x transpose time y minus x for all x and y in the domain of f. The critical point analysis. Sports Qx star plus C equals 0, which implies X star equals negative Q inverse C when Q is invertible. So, Hessian second order condition. The Hessian of the quadratic function is constant. The Hessian of f of x equals q. So the convexity characterization in Hessian will be q positive semi-definite, f is convex and a global minimum is guaranteed, q positive definite which means f is strictly convex and the global minimum is unique, q indefinite which means f is non-convex and may have local minima. Now talking about Karlsruhe-Tucker KKT conditions. The KKT conditions are a set of conditions that characterize optimally in constraint optimization. For convex problems, they are both necessary and sufficient for optimality. They consist of four parts. First part, primal feasibility, which is represented as g sub I of x star is less than or equal to 0 and at sub j of x stars equals 0. Second is dual feasibility, which is represented as lambda sub I is greater than or equals to 0 for I from 1 to m. Third condition is stationarity. The gradient of f at x star plus the sum over I of lambda sum I times the gradient of g sub I at x star plus the sum over j of m sub j times the gradients of h sub j at x star equals 0. The fourth condition is complementary slackness, which is represented as lambda sub I times g sub I of x star equals 0 for I from 1 to m. So here's a solution done for a simple problem for unconstrained quadratic minimization. So a quadratic function is taken where x is the variable vector, q is a symmetric matrix, and c is a vector. So the goal is to find x dot that minimizes fx. So first, the gradient of fx first order condition is j. The gradient as the gradient shows the slope of the function at a minimum slope is 0. Then to check convexity, the Hessian of fx is computed. Then the definiteness of q is checked, whether it is positive definite or positive semi-definite. So here are some of the code implementation examples. Three examples has been used. So the first example is of quadratic optimization in 2D. So what is the code does is first it defines variables. So x is a vector with two unknowns, that is x1 and x2. And then the problem is defined, that is the matrix Q equals to 2, 0 and 0, 4, which represents the curvature, that is positive semi-definite, so the function is convex. The vector C equals to 1, 2 represents linear coefficients. And the objective function is minimize a quadratic function of x. And the constraint is also defined. Problem is solved using the props itself. And then the visualization is shown like this. So the second example is applicable in finance sector. It's a portfolio optimization. So the set up portfolio problem is set up three assets set with risk, that means covariance matrix sigma, and then the object is a CP variable and represents portfolio weights of how much to invest in each assets. Similarly, objective function is created because we want to minimize the risk, and then constraints it's created. Then the problem it solves. What it does is it finds the portfolio allocation that gives the minimum risk and prints the minimum risk and portfolio weights. So the visualization is created as with bar chart. It shows how much weight is given to asset 1, asset 2, and asset 3. So the last example is of quadratic constraint. So first variable is defined. It's a 2D vector with x1 and x2. Then objective function is defined. Same with constraints, and it's solved, which tries to find the point inside the circle that's closest to the origin, and it prints optimal value and point. So the visualization draws a circle, so it's a circle, and optimal solution is marked in red, which sets equal scaling for proper geometry. So convex optimization can be applied in different cases. So first is in sector of machine learning. Uh, we can see it in SVM, support vector machine. The problem of finding the base separating hyperplane between two classes can be written as a quadratic programming problem. Convexity ensures that the margin found is the largest possible and the solution is globally optimal. Similarly, with regularized regression, ridge regression or L2 penalty as a squared weights term to the loss function, making it strictly convex and ensuring a unique solution. And lasso regression, that is L1 penalty, promotes sparsity in coefficients, helping in feature selection while maintaining convexity. Similarly, with natural neutral training, it is its partial convexity is involved. So while deep neural networks are generally non-convex, many individual components are convex. Loss functions such as mean squared error, cross entropy are convex. This convexity helps guarantee that optimization algorithms converge well in simpler models like logistic regression. Now, in sectors of economic and finance, first, portfolio optimization. For this, Markowitz model is used. So it uses quadratic programming to balance expected return versus risk, the variance of returns. The covariance matrix of assets defines the quadratic risk term, making it a convex optimization problem. Then there's asset allocation. So when distributing wealth among assets, convex optimization ensures that the portfolio respects constraints such as budget, minimum or maximum investment levels, and risk limits. Similarly, it can also be used for risk management. For example, value at risk and conditional value at risk can be formulated as a convex problems, ensuring robust solutions for financial risk estimation. So, in case of data science and analytics, principal component analysis, it uses finding principal components reduces dimensionality by solving an eigenvalue problem which is convex. This makes PCA both efficient and reliable for large datasets. Similarly, for clustering, K-means clustering is not fully convex, but subproblems like updating cluster centers are convex. Spectral clustering relies on convex eigenvalues decomposition for graph partitioning, and for feature selection, using L1 regularization like in Lasso creates sparse solutions which automatically eliminate irrelevant features while keeping the optimization convex. Now to sum it all up, convex optimization with matrices is the study of optimization problems where both the objective function and constraints are expressed in matrix form. A problem is considered convex when the objective function is convex and the feasible region is a convex set. Strict convexity is especially important as it guarantees the uniqueness of the solution. Positive semi-infinite matrices play a central role in verifying convexity, particularly in quadratic formulations. One of the strongest advantages of convex problems is that they always guarantee the existence of a global optimum. This is in contrast to non-convex problems which may have multiple local minima and can trap optimization algorithms. Mathematical tools such as gradient, first order derivative, and the Hessian second order derivative matrix are essential for analyzing convexity and identifying optimal points. Additionally, the Karus-Kuhn-Trocker KKT conditions provide the necessary and sufficient framework for determining optimality in constrained convex problems. On the practical side, modern libraries such as VXPy, NumPy, and Matplotlib make it possible to implement and visualize convex optimization problems efficiently. These tools bridge theory with practices, allowing us to apply convex optimization across fields like machine learning, finance, and data science. And these are some of the references that I used for the information presented in this presentation. Thank you.